Hi everyone, welcome to the SPREE seminar. It's my great pleasure to introduce Dr. Navid Haghdadi. He recently completed his PhD at the end of last year, received his PhD from UNSW, and he studied under the supervision of Ian McGill and myself at SPREE, and he's now employed as a postdoctoral researcher in the Centre for Energy and Environmental Markets at UNSW, and he's employed across both electrical engineering and SPREE. And he's here today. He's got an incredible set of skills in big data analysis and modelling, which have been very useful across a number of our projects, and he's been harnessing those skills to look at integration of renewables, both at the distribution level and also the system level. So he's got plenty of things to talk about, so I'll just hand straight over to Navid. Welcome. Thank you.
Hello everyone, thank you very much Anna for the nice introduction. Okay, so I'm going to talk about some of the things which I've done in my PhD and also briefly about the things which I've been doing after my PhD. So this is the title of my presentation, which happens to be also the title of my thesis, my PhD thesis. And just to give you a little bit of the context, as you know, we have incredible number of smaller scale PV systems in Australia at the moment. So this is a chart taken from APVI website. So it's the last updated number is for June 2018, 3 months ago, and it's already out of date because it's 3 months ago, and we have 8.45 gigawatts of PV systems, mostly residential, smaller scale systems. Just to give you more insight about the period of my PhD, just let's have a look at some of the important dates. So my PhD was awarded at the end of last year, 2017, December. And since then, we already had about 1.5 gigawatt more PV systems. I submitted my PhD in April 2017, and we had only 6.15 gigawatts of PV systems. So you can see even after finishing my PhD, we had almost more than 2 gigawatts of PV systems. The first draft of my thesis I've sent to Anna and Ian was 2016 December, and it was much less. And this is the time I've started my PhD. We only had 3 gigawatts of PV systems in Australia. So imagine this is the story of my PhD. So I was gonna work on this stuff, and when I started, it was only 1/3 of what we have now. And this is, by the way, the time which I've sent that first email to Anna asking about if she has any PhD position, and she kindly replied and said, yes, I'm interested, and just please apply through UNSW. And I've applied, and thank you very much, Anna, for responding to that email. That was very good, and that was the start of a new era in my life, and I came to Australia. Anyway, that was a separate story. Let's talk about my PhD. So at the moment, as I said, I can safely say that we have around 2 million small scale PV systems already in Australia. And Australia is the world's leading country in terms of residential PV systems. Okay, just a little bit more on the context. This is again the same sort of chart, but just break down by the different size categories. I should say that probably one of the biggest challenges of small scale PV systems in Australia is about lack of information about their performance, operational performance, and also about their controllability. So we don't have any control, and we don't have enough monitoring on these small scale PV systems. So that's why we need a better estimation for about how they perform in Australian electricity networks. So this is the same chart as I said, and we can say that around 75% of all PV systems are in this category, less than around 10 kilowatt. So we can say that this is residential systems. And just to give you an insight, this is what it looks like to be in a residential PV system. So you can see that all of these residential systems, each one has a different orientation, different characteristics. You can see that they must have different module types, different inverter types, different shadings, different operational conditions. So that's kind of the main aim of doing my PhD. So we sort of separated the steps of my PhD in 3 different categories, 3 different steps. The first was just to work on the sample data. We had some sample PV performance data from a publicly available data set, which I'm going to talk about that later. And then the first step was just to make sure that this data is good enough for doing this analysis. And the second stage was to just come up with some ideas to upscale this PV system sample performance data and aggregate them and see that how much it could generate by the whole systems in Australia and in different locations, in different networks. And the last one was about, now that we have an estimation of the contribution of PV, how much we could see in terms of their impact on the electricity network. So that was, seems easy, but it wasn't. So this is, I can say that that was an impossible mission. And I had slightly higher hair back then when I started my PhD. And by the way, you can see that the solar cells in the background as well. Yeah, so let's talk about the first step. So the first step, as I said, was about looking at the quality of the data, the PV systems data. So we grabbed performance data from a publicly available website, pvoutput.org. And the data was about for about 5,000 systems for about 5 years. And as an estimation, at the initial stages, it was about 300 million records because it was 5-minute data. And then we applied a set of filtering methods in order to improve the quality of the data. And so this is the sample size. I apologize if the fonts are small, so you probably can't see the dates. But this is throughout my PhD, and the sample size was increasing because more PV systems were becoming available and we could have access to them as well. That was another challenge in my PhD. So as I was going in my PhD, then more data was becoming available each year. And it was good in a way, but I had to redo most of my analysis again. And yeah, so a set of filtering things which we apply. So for example, if we wanted to catch the monitoring issues. So this is, for example, one example of one system which you can see here. We had some issues in the performance of the systems, or this one could be just an inverter trimming, or this one could be just the monitoring issues when you have the repeated values. And in addition to that, we also checked the characteristics of these systems as well. So for example, tilt and orientation of all systems, so we can compare it with the actual condition in Australia. So there was a lot of computational work and working with big data, and I can say that it was again very hard. So I was fit back then, 4 years ago, so I could do this, and I worked a lot with computers. Anyway, so and the next step was just again increase the quality of data through looking at the metadata information of the systems. And by the way, we presented this work in Asia Pacific Solar Research Conference a few years ago. And I'm not going to go through a lot of details in these presentations because I thought that I can give you the overview of all of the things, but you can always refer to the papers, and the slides will be also available through SPREE's website. So you can go and have a look at all the boring stuff in the papers. Yeah, so we had sourced the Clean Energy Regulator data, which has all the information of all small-scale PV systems in Australia, including their postcodes and module brand, PV brand, the inverter brand, and also the date of installation. So we had we did some comparison between our sample and whole PV systems in Australia to make sure that this can be considered as a relatively good sample of the whole PV systems in Australia. And again, we had compared the age of systems, for example, the size range, the location of systems, and the location in terms of the weather conditions, and also the inverter brand and other informations. So as you can see that we could fairly say that they are similar. So we can say that the analysis based on this sample can be useful. And by the way, that was the best and only available set of data set which we could use. And also we compared the performance of these PV systems with a set of utility monitored PV systems kindly provided by Osgrid. And so which showed that the performance is also similar to what Osgrid is also claiming. And also this is, for example, the percentage of systems with the inverter to module size ratio. So for example, it's about 80% of the systems where the inverter size was less than module size. And it was different in different states as well, which could be due to different rules applied for promoting solar in different states in Australia. Anyway, so the next step was just, in addition to check the quality, we also tried to come up with some ideas and some methods in order to estimate the metadata of these PV systems. So this is a method which we published in Renewable Energy last year, and it was about how we can use the output data, output power, output generation of PV systems and use the PV modeling stuff in order to estimate the parameters of the installation parameters, which is tilt, orientation, and location of PV systems. So this wasn't the rocket science, it was just using the available PV simulation packages, but we're using it in reverse. So in normal condition, you usually use the PV system modeling packages. You give the weather condition, weather data, and also the installation parameters, and get the output for a typical PV system. But we used it in reverse. We gave it the output data and tried to estimate the input parameters. And then it was good and fun, and we tested the method on 3 different case studies. The first one was a simulated set of PV systems using the meteorological data in Australia for different regions in order to just cover all possible tilt and orientation. And the second was some PV systems with validated parameters. And the third one was all of these PV systems from pvoutput.org with self-reported installation parameters. And you can see that the error for these case studies were also acceptable and good. And as I said, the detail of this paper, we can refer to that paper as well. The next step was just moving from the metadata to the actual generation data. We tried to have a look at the performance data of this sample and then compare it with the publicly available performance data and also publicly available estimates of how distributed PV systems are performing in Australia. So we compared these sample systems with 4 different available modeling packages. The first one was the Renewables, the one which is used in Renewables Ninja, which is an open source model using NASA mirror array analysis data. The second one was PV Library, which is Sandia National Laboratory's simulation package, and we used it with RMY and TMY weather data. And also we compared it with the average estimates from Clean Energy Regulator and Clean Energy Council, which is used for solar promotion in different states. So first, before doing that, we had a check if because the data was for specific years, we checked that if the data and the performance, the solar exposure is similar in different years. So the quick analysis to quick comparison between years, and then also looked at the performance and average daily yield for all of these systems in Australia. So this is the 25%, 50%, 75% and values for the daily yield of all of these PV systems. And for the comparison, so here you can see all the cities, the major city, the capital cities, in using different models as I described. So you can see, for example, for Darwin, we had less number of systems, only 10 systems. So the result of, the performance of the sample was a bit different. But for regions which we had more systems, the performance was quite similar to what is available through the modeling packages and also other estimates. But still, it's different. And also, you can see that the ideal set as well. And we try to separate based on their tilt and orientation. We try to separate those with good tilt and orientation, near optimal tilt and orientation, from others to make a better comparison. And the results for other cities can be seen as well here. So, so this figure shows all of these comparisons in one plot. So you can see that for each city, the distribution and also the values for available. So the main points which we can get from this research was that generally Clean Energy Council estimates and also estimates using PV library using RMY and TMY are more aligned with the ideal subset, not with all systems. But Clean Energy Regulator is somehow underestimating the ideal systems, which we can say that is more aligned with the majority of systems, not only the ideal systems. And Renewable Ninja is generally overestimating the performance, which is not surprising because it's using NASA data, which is known to be overestimating Australia. And again, you can refer to the exact numbers and errors in the paper if you're interested. I'm gonna go to next slide. And I'm going to talk a bit about the APVI mapping tools as well here. This is something which was aligned with my PhD, and I was able to contribute in some of the works in live solar PV as well, which was great. And I strongly encourage you to check this out, this website. This is a great website with lots of useful information about the solar potential and solar status in Australia. And so I was involved in the live solar PV a bit to prepare and to just doing some pre-processing on the data. So as an example, you can see that, if you can see, it's the screenshot of the main page of the live solar PV. So you can go there and you can see the 2-digit postcode performance and a state level performance and also the state contribution. So I'm talking about this because it's somehow using, and we have been implementing this using the same methods which I was using for my PhD. And the method is that once you've come up with your sample, once you've done the pre-processing and you were comfortable with the quality of the data, then you can use that and upscale that using the installed capacity in any region to estimate the overall performance and aggregate generation of PV systems in any region. So the idea is simple, and it's using the available PV systems performance and then upscale it by the capacity installed in that region. And then we can estimate the contribution of PV in peak, for example, as you can see in this figure, for example, is for New South Wales yesterday. So you can see that this much of the load. So we're getting the load data directly from AMO website, and then also the PV is upscaled. Then you can see that how much of the load has actually been contributed by PV. And then you can estimate the contribution of PV. So using this method, I've done some analysis about the actual and the expected performance of and the contribution of PV systems, distributed PV systems in Australia, including in zone substation level, the feeder level, and also the estate level. So the first one was on the zone substation feeder level, which you can see that again the same method. So we had the data, and we also sourced the load data from zone substations, from all zone substations in New South Wales, not all of them, most of them, in Osgrid area. And then we also had the information about the installed capacity in each zone substation, so then we could estimate the contribution of PV in each zone substation. So this figure here shows that how much PV how much load has been reduced likely by PV when the PV penetration was changing. So this each dot shows one zone substation, and the different colors representing different years, because we used 3 different years. And then you can see that how much we had peak reduction. For example, this one could be 3%, and for this zone substation, and we had 5% PV penetration in that zone substation. So we can see a relatively good trend in having more peak reduction with having more PV. But another type of a study was that to just try to, once we had the contribution, we had an estimation about the contribution of PV, then we could change the penetration of PV and simulate that what could be the impact of PV in different penetration levels. So for example, this figure shows, the blue one shows the peak reduction potential, and if we had 10% peak, 10% PV in each zone substation. So again, you can see that in some zone substations, we have a great potential for reducing the peak, and in some not. So this is important because we can see that how much it is different, the impact of PV could be different in different zone substations, even within one climate region, which is New South Wales and Sydney area. So you can see that it could be quite different based on the different load profiles. And also when we go to higher levels of PV penetration, we can see that it's actually the impact could be reduced. Yeah, so the next figure here shows a very important thing. So one of the challenges in our work was always that what is a peak? So when we say about the load peak, we can say about one time stamp in the year, or we can say about top 5% or top 10% of the time stamps, and it can have a huge impact on all of our further analysis. Why? Because when you go to a very limited number of zones, peak times for the zone substations, it could be very random behavior. So we've done the same analysis. This time, I've changed the number of peaks to be considered for each analysis, and then try to also did this for 23 zone substations, which we had more than 1.5% peak reduction. And then you can see that for the first, for example, when you consider only 0.1% of the times, which is about 35 time stamps, and it's 15-minute intervals, so it's about 10 hours or less, 8 hours, you can see that 8 hours of the peak time, you can see that the behavior is changing a lot. But when you go to 0.5%, which can be about 40 hours of the peak times, then it seems to be stabilized. So, so we decided to go ahead with something between 0.5% and 1% of the times. And by the way, if you go higher than that, you reduce the value of peak, because we are talking about the very small number of time stamps and those who are important for the network. And usually the network is built in order to meet those very limited number of time stamps. And the next thing which we've done was to characterize the behavior of PV systems in different zone substations. So as I said, in different zone substations, we had different contribution of PV. So we thought that maybe we can plot the PV performance in the peak times of each zone substation, and then see that how much is changing. And then we try to cluster this behavior into 5 different categories. So this figure says that, for example, cluster 1, which represents, for example, 30 or 40 zone substations, we have a fairly consistent PV availability in all of top 1% of the peak times. And then for cluster 2, we have again somehow consistent behavior around 40% kilowatt hours per kilowatt. But it's slightly lower than cluster 1. And cluster 3 and 4 are interesting because they're showing that in some of the zone substations we could have higher availability in the first peak times, and then slightly lower in the next peak times. and also for cluster 3, lower in the first peak times and higher in the next peak times. So for example, the cluster 4 could be some zone substations with a limited number of peak times in summer, and then the rest of them could be in winter. So we can reduce the first peak times, but we can't do anything for the next peak times, and vice versa for cluster 3. And cluster 5 shows probably some zone substations with all winter peaking behavior, which PV is not available in their peak times. And then this is the load duration curve for all of these, for 4 clusters, cluster 1 to 4. Again, you can see the different behaviors. This is for different levels of PV systems. So cluster 1 again shows that if you increase the penetration of PV systems, you can see a consistent behavior and consistent peak reduction. But in cluster 2 and 3 and 4, the behavior is different. And the main point of this figure and this paper was to show that different zone substations are different in terms of their capability to accommodate PV systems and the impact of PV on them. And PV can play different roles in different zone substations. The first one could be for peak reduction. The second and third one, they could be different in terms of how PV can contribute in their peak reduction. And in this figure, because in some of the studies, the previous studies, they tried to find some guaranteed level of PV performance. So for example, AMO published some reports about the wind availability in the peak times. And we say that, okay, we know that in 1% of the load peak times, in how much of the times we can be sure that at least we have, for example, 40% of capacity. So this figure, for example, here, the first one is for 2013. So you can see that, for example, in this zone substation, the very first zone substation, we can say that in 90% of peak times, we can have at least 30 kilowatt per kilowatt peak performance, which means that for these zone substations, for the 90% of the peak time, we can rely on at least 30% of the capacity of PV. And then again, it's different for different zone substations. Again, you can see that it's decreasing in zone substations. And if you go to higher level of certainty, higher level of capacity assurance, you can get lower number for the percentage of peak time. And also it's interesting to see that it's different when you use different years as your data sets. So for example, if you look at 2015, the general availability was higher. Why? Probably because of the load, a different load behavior in 2015 because of the shape, the change in the load shape, or because of the change in the PV or weather or anything else, or the correlation of peak and PV. So that highlights the importance of more analysis on the potential impact of PV on the peak time. And the second figure here, it shows that red line above, but just that red line, but we also simulated what if we had some capability of shifting the load, because this is again important with introducing lots of battery in the system. We can anticipate that we could have, for example, 1 hour of load shift availability or 2 hours of load shift. So again, we did the same analysis, and we can see that when you have 1 hour load shift, you can actually increase this percentage of time, but some amount. And again, it's different in different years and different in different zone substations, which is again important and interesting. And again, if you're interested, you can go to this paper and look at more nice figures. And the next step was about somehow similar analysis, but this time on looking at the big picture about the whole estate. So we used again, we upscaled again the PV performance to the whole estate, and we looked at how much the gross and net load are different in different estates. And the gross load is the underlying demand which could be there had there been no PV installed. And the net load is the current net load. And you can see that, for example, it is again different in different estates. So Queensland, for example, showed higher reduction in their peak, whereas its New South Wales is slightly lower, and in Tasmania is lower as well. And this is the top 0.5% of peak times again. And this figure shows the change in the time of peak. So again, it's interesting how much PV could change the time of peak, the daily peak time. And so again, for example, you can see that in Queensland, it's shifting to the afternoon in always all peak times. But in Victoria, we had some shifting to morning and some to afternoon. And New South Wales more to afternoon. And we have something going on in South Australia, probably some control load there. And also in Tasmania, we don't see many shift here. A lot of peaks are here and they don't shift, but we have some shifts here and here. So again, it's highlighting the importance of, and also you can see that in different years, the impact could be different. And it requires more analysis. This is again showing, again similar to the zone substation level, but this time for showing that how much the average peak could be reduced in different penetration levels. And I also use these field dots here to show the current status. But I should say that this is for 1.5 years ago, so it's changed now. But you can see that again, this is actually looking at all days, and this is the same thing for only 10 peak days, only top 10 peak days. So first of all, you can see that when you look at all days and look at only top peak days, it's different. Again, highlighting that PV can help more in the peak days. And the second takeaway is that in some states, we have more potential for peak reduction, but in some states, we could be reaching to the saturation limit, which means that we can't reduce the peak demand with PV anymore, maybe in coming years. But this is just using the sample and for 3 years. Yeah, so this one, again, continuing the same analysis, this one using different penetration levels. Again, showing that if you remember, we had this for different clusters for zone substations, but a similar behavior in different states. So we can see that it's variable. The pattern of reduction in the load duration curve, this is the load duration curve with different PV penetration level. And you can see that how much it could be different in different states. In Tasmania, for example, it's totally different to Queensland. And then this one is again showing the impact in a slightly different way, this time, but it's similar to what I've presented for the zone substation. The top graph shows that the percentage of time in top 0.5% of demand and the availability of PV performance. So for example, here, it shows that if we look at 50% of the top time, we can say that we have at least around 42% of PV performance in New South Wales in 50% of the time. But for Victoria and for South Australia, we had higher, we have more than 50% average performance over at least 50% of times of the peak demand. And the below figure shows similar thing, but this time for the top price timestamps, because it's also important. The first one is the peak demand, and the second one is just about the top 0.5% of price and times in the year. So again, we can see that we have less available PV system in the top expensive and high price times in the NEM, which is probably because PV has already reduced the cost in other times, and it can't reduce more where we have high price. And so in some of these high price events, we don't have PV availability, and that's the reason we have high price. So that could be also looked at in this paper, which I've presented in the IEEE PES conference last year. Actually, I didn't present this, but you can find the paper. It's indexed in IEEE. I couldn't go to USA because of some silly reasons, and a silly person in US who happens to have a huge amount of power. Anyway, so I couldn't go there, but the paper is indexed in IEEE. Anyway, so we always find ways to do our work. And yeah, so that concluded my work which I've done in my PhD. So in summary, a set of techniques to improve the quality of the data, and then come up with some ideas how to estimate the aggregate PV generation and also look at the impact of these PV systems in quite different range of ways. And so I finished my PhD. I can't say that I was saved in my PhD. So I'm not sure how much mess I left behind, but I finished, but I'm just joking. It was a great PhD. I had lots of fun. It was great. And you can see that all of us are very happy. And I should take this opportunity to thank my supervisors, Anna Bruce and Ian McGill. Ian is not here. He's overseas at the moment, but he promised to watch the video. Hi, Ian, in case you're watching this later. And thank you very much, both of you. And so I'm going to talk about a little bit about some other works which we've been doing. As a side project, for example, I've been doing some cool things about developing an open source tool in order to analyze and design the tariffs for electricity networks. So this is something which you can go to this page and find the source codes and all the information about this project. So basically, this is a GUI built in MATLAB, which I've built in order to be able to play with the model. And you can actually import your own load data or use one of the pre-existing load data. You can filter it based on the demographic information and then apply any electricity network tariffs and see that how much the bill can be changed by different tariffs. And then you can do a lot of analysis on this. For example, you can see that how much the bill is correlated with the contribution of for example, contribution of users in the peak times. And then I should say that we are going to convert this to Python as well with the help of a new research assistant, which we have, Nick Gorman. So I have one Superman helping me. So now we can do lots of interesting things together. And while you are here, I also wanted to introduce this new page in our CEEM website, which is about our open source tools. So we have a range of other tools, including the NEM data tool, which is built by Nick Gorman, which is a very cool GUI. You can go there, you can get any of available data sets in the AMO website, because we have lots of publicly available data sets, but it's very hard to get them, very hard to filter and just acquire what you need. So this open source tool helps you to use it and find the required data, which is very nice. And he's going to add some statistical analysis to it as well, which could be very nice and helpful for all range of researchers. And also we have some other tools, including the local solar sharing scheme model built by Luke and Naomi here. And please go to this website and check, and also check the tariff tool. And if you have any suggestions, if you have anything you want to contribute or you want to improve these models, we are more than happy to collaborate on any of these. And quickly on other collaborations which I've been doing in my post-PhD era. So we are involved in a project with ITP Uni Melbourne, which is an ARENA-funded project to develop some open source capacity expansion modeling, which lets users to go there in a very nice GUI. They can play with the parameters and they can run the simulation and see that what would be the least cost scenario for future, which is a very expensive at the moment if you want to buy one of these available packages. But this one could be very interesting and it's publicly available and open source. The other one is my work with Rob Passy, which is about designing cost-reflective tariffs, and our work with Naomi, which is about the security implications of distributed PV systems, which is again using some upscaling methods in order to see that how much these aggregate PV systems could have done in the system events. So, for example, recently we had a very interesting event in all of Australia, a frequency excursion. In some states it was over frequency and in some under frequency, which was very interesting to see that PV systems, how they respond to this event. And it's actually very interesting for AMO as well to see that how they can manage this uncontrolled behavior by a huge number of PV systems. my collaboration with USAC is not here, and about some capacity expansion modeling for Indonesia, and Mike in PVs in apartment buildings, which is again interesting because most of the systems are in houses. So in apartment buildings, we need much more work in order to make sure that apartments can also have good PV systems. With Anam about the contribution of aircon and electric water heaters in the peak demand, and Abdullah about working in, again, scheduling load and generation. And as I said, Nick Gorman is also doing some great work in simulating an open source model for simulating the NEM dispatch tool, which is very interesting to see. And also we have a new PhD student working on the intelligent transport system, which is great. So I'm sure Ziv will manage to catch all of these guys and they will present their voice here one day. And yeah, so we have a great team in CEEM. So that concludes my presentation, and thank you very much, and I'm happy to take questions if you have any, if any of these things made any sense.
Nice talk, very excellent work, thank you very much. I was just wondering about how comprehensive is the collection of what PV systems are on the grid. I think you're probably not counting mine, because I think you can't know about it.
So yeah, so you mean about their information. We have actually, we have access to the Clean Energy Regulator database, which has the information about their module and inverter brand and model, and also their postcode and the installation date.
Only if they were told about it.
Sorry?
Only if they were told about it, I think. Yeah, how would they know about mine? No, I don't get STC. You burnt my bridge. Yeah, you can only get one bite. Yeah, I think they don't. There might be a lot of systems out there that aren't being counted.
Yeah, there could be, yes, yeah.
And I'm shifting my load too, with a battery, so.
Yes, exactly. Yeah, that's another challenge which someone else should be looking at. And it's, even if they are reporting this system, they still don't have any information about their behavior and their performance. Just, yeah, that's even worse. Yeah.
Thank you, Navid, for a very interesting talk and for your research. Very exciting. I have two questions, if I may. One is a bit more general and the other one is a bit more technical. So you've shown this APVI map. We almost have more than 2 million dwellings now.
Yes, yeah. We can formally say this in probably 10 days when the next report of CER is available.
So from your overall experience, when do you see this market's gonna stagnate, and what percentage of the freestanding household market is actually wanting to get PV? And I'm sure there will be some that may not bother buying a PV. When do you think this is gonna kind of stagnate?
Yeah. That's a very interesting question, and actually I guess in the next coming years there could be a lot of issues relating to this. As I said, for example, AMO is thinking about the potential impact. So at the moment, it's 2 million systems. It's about 20% of houses in Australia, and still they have a lot of issues about how their systems are performing. So in addition to the households' choice, I guess also the network providers and the network operators, they will come and do something in order to just manage this. So then the trend will change based on the decision of the network operators as well, because there should be a saturation limits about the number of PV systems importing to the system. And yeah, so I don't know, in different regions, different networks, there could be more potential, and in some regions, maybe in just 1 year or 2 years, maybe some network operators, they just put something to stop increasing the number of PV systems.
Okay, actually this ties into my second question. So you've shown the plots about different zone substations and PV having different impacts. You've had 5 clusters. I was gonna ask, what is the reason behind PV's different impact on these different zone substations? Is it timing of the peak, climate, or what's?
Yeah, it's because of the load shape in those peak days in those zone substations, both the peak time and also the value of peak. So some of them have very, for example, a small number of very peaky times in some very hot weathers, but then rest of their peaks are in winter evenings, for example. So that's a different behavior than a constant industrial load, which has always similar and flat load profile in some zone substations. So that makes this different. Yeah, no problem.
Follow on question from that. I think in Queensland that any system over, I think it's 20 kilowatts or something, has to be wired so that it does not export any electricity. But from what I understood about this peak management, that I'm surprised that people don't make the argument that if you actually have that data from the substation, that it would actually be beneficial for the PV system to be exporting during peak times. Does that make sense?
Yes, yeah. For many zone substations, still we have lots of potential for peak reduction, including, for example, in New South Wales a few months ago, they introduced some schemes. For example, Ausgrid, they said that they will pay 200 per kilowatt, I guess, or something like that, for people who install PV system in some of their zone substations, because they believe that they can reduce the peak in those zone substations.
Okay, well, Ausgrid's doing that, and in Queensland they're doing the opposite.
It could be because of, I'm not sure about that plan, and I'm interested to know more about this, but it could be because they analyze the performance of PV and they think that in those specific zone substations, PV cannot contribute any in the peak time. And
Ausgrid's the only one that you know of?
Yes, yeah, Ausgrid is doing that, but for some zone substations.
Right.
Just a comment on that, I guess there might be other motivations other than the technical motivations, but financial benefits to particular parties who have competing generation.
Exactly, yes. Yeah. Any other questions?
Okay, so are there any final questions for Navid? No. Okay, well, thank you everyone for joining us. Please join me in thanking Navid for that very interesting talk.